Hello and welcome back to Calculus, the series where we explore derivatives. You already know. First, I'd like to thank all the nice people that support this channel by liking and subscribing. Now, as promised, today we will take a look and compute the derivatives of 6 complex functions, employing all differentiation rules we've covered in parts 4, 5, 6, and 10. So let's immediately get to the first example. Here is a function given by f of x equals to x cubed times tan 3x. You can immediately see here we will have to employ the product rule since we have the multiplication of two different functions. As a reminder, I put the formula right here. Now this tells us that we need the derivatives of x cubed and the derivative of tan 3x. Immediately we can see the derivative of u, or in this case x cubed, is simply 3x squared. And then the derivative of v is going to be secant squared of 3x. However, here we also have to use the chain rule because we have a function inside the parentheses 3x, and its derivative is simply 3. Well, now that we have all the 4 components, we can put the derivative together. This is simply going to be 3x squared times tan 3x, and then we add x cubed times 3 secant squared of 3x. And this right here would be the derivative function. This wasn't so difficult, so let's immediately move to the second example. We are given a function f of x equals to 1/3 secant cubed of 2x minus secant 2x. Here, no product rule is necessary. However, we will need to use the chain rule since we do have another function in the parentheses. However, before we get into that, I'm just going to quickly tell you that the derivative of secant is going to be secant x times tangent of x. If you don't believe me, you can simply rewrite secant as 1 over cosine and then do its derivative with the quotient rule. And then after simplification, you will get secant times tangent. With our function, however, I can tell you we have 3 different layers. Because first, we have to apply the power rule for the cube, then we have to multiply it by the derivative of the secant 2x, and finally we have to multiply it again by the inside of the secant, basically the derivative of 2x. So let's do this step by step and first apply the power rule to the first part of our function. Here I've applied the power rule, so the 3 goes in front, and power minus 1. Next, I need the derivative of the secant, and we already said that is simply secant x tan x, only instead of x, we have 2x. And finally, we need to multiply by the derivative of 2x, the innermost function, and this is simply 2. Now, for the second part of our function, this is simply secant 2x. So you can probably see this is just a repetition of this part. Finally, let's do some simplifications. For example, 3 and 1/3 cancel each other out. And also, we can factor secant 2x tan 2x times 2 outside the parentheses to make this expression nicer. And of course, all that's left in the parentheses is going to be secant squared 2x minus 1. And this right here, once again, is the derivative of our function. A little more complex, however, still very manageable. So now let's move on to the third example. We are given a function f of x equals to the natural log of x squared plus ex. Once again, This function has two layers. You have the natural log and everything that is inside the parentheses, meaning that we have to use the chain rule. However, firstly, as a reminder, the derivative of the natural log is simply 1 over x. And of course, the derivative of the function e to the power of x remains e to the power of x. Now that we know this, we can continue computing the derivative of our function. Firstly, the derivative of the natural log is 1 over, and everything inside the parentheses we just copy paste, so 1 over x squared plus ex. However, since we do have a composite function, we have to multiply this by the derivative of the inside. Inside we have x squared plus ex, and this derivative is simply 2x plus ex. And of course, we can always rewrite this in a nicer and more compact way as one fraction. And this here is our final answer. Wasn't so difficult, so now let's move on to the fourth example. For this, we are given a function f of x equals to ex ln x. Here you can immediately see we once again need to employ the product rule since we have the multiplication of two functions. So here I'm going to skip all the mini steps and immediately get to the derivative. First, derivative of ex remains ex, and we multiply this by the original ln x. And then we add this with the original ex multiplied by the derivative of the ln x, which is 1 over x. And once again, we can always rewrite this in a more compact manner. This was quite easy, so let's immediately get to example number 5. Here, we have a function f of x equals to ln x over ex plus 1. Now, since this can't be simplified in any way, we have to apply the quotient rule. Here, as a little reminder, I put the formula for the quotient rule. So now we need our four components, the u, the v, the u prime, and the v prime. For the derivative of ln x, we know that it's 1 over x. And the derivative of ex plus 1 is simply ex. 1 becomes 0 because it is a constant. Now that we have all four components, we can just put them all together. And this massive fraction right here is the expression for the derivative of f. There's basically nothing to simplify, so we can just leave it like this. Now, leaving the best for last, let's move on to the final example number 6. Here, for the final example, we're given the function f of x equals to e to the power of arcsine x times the natural log of sine x squared minus 3 to the power of x. This is a complex function. First, we do have to use the product rule since we have the multiplication of two different functions. Next up, we will also have to use the chain rule since e is raised to the power of another function, arcsine, and inside the natural log, we have sine of x squared minus 3 to the power of x. And of course, the chain rule will have to be applied multiple times since inside the sine function, we have another function, x squared. So first, setting u as e to the power of arcsine x. This means that u prime is going to be equal to e to the power of arcsine x, and then multiplied by the derivative of arcsine. And as we discussed before, its derivative is going to be 1 over the square root of 1 minus x squared. We then set v as the second part of our function, ln of sine x squared minus 3x. And its derivative is going to be extremely complex. First, we do the derivative of the natural log, so we have 1 over sine x squared minus 3 to the power of x. We then have to multiply all of this by the derivative of the inside. First, derivative of cosine x squared. Sorry, sine x squared. Its derivative is going to be cosine x squared, and then we apply the chain rule again. So we have to multiply this by the derivative of x squared, which is going to be 2x. And then we subtract the derivative of 3 to the power of x. And as discussed in part 10, this derivative is going to be itself 3 to the power of x and multiplied by a coefficient ln of 3. Now finally, we have all of our 4 components, meaning we can write the expression for the derivative of f. The first part is going to be e raised to the power of arcsine x multiplied by 1 over the square root of 1 minus x squared. And we multiply this by the original v, which is the natural log of sine x squared minus 3 to the power of x. And then we add this with the original u multiplied by v prime. And this entire monster here is going to be the derivative of f. Trying to simplify this just doesn't make sense, so we can just leave it like this. Of course, I hope these 6 examples were helpful for you to see all the differentiation rules in action. I will discuss the implicit differentiation in the next video, and also show you where the derivative of arcsine x comes from. And naturally, together with arcsine x, you already know there are 2 more inverse functions, namely arccosine and arctangent. So I hope to see you there, and have a nice day. Bye!